So welcome to your first video of severe weather for geoscience. We haven't done a lot of videos in our class this year at all, and so introducing you this just because I'm not around to give you notes myself and to give you something to keep us on schedule to be able to get into severe weather and tornadoes more so next week. What I want you to do is take the notes down here into your notes just as if we were in class. And then there are a couple pages where you have diagrams to add things to, add labels to, and add other information to, like we've done other times in class too. But the first few things you'll need to put somewhere else, just into a fresh spot in your notes to start out this new unit on severe weather. What we're going to look at with severe weather is primarily thunderstorms. We won't get into too much to hurricanes because they don't affect us here in North Dakota, but thunderstorms, tornadoes, hail, those kind of things are very common around here, and it won't be long at all before we'll be getting thunderstorm season underway in North Dakota. So visit these as we finish out the year, and starting out with thunderstorms kind of as a broad topic, and then we'll get into specifics like tornadoes toward the end. Thunderstorm ingredients. Basically, for a thunderstorm to form, there are three necessary ingredients, and they're all pretty important to get thunderstorms to be possible, but probably the first one is most important of all, and that's really the fuel for the storm. Now, I'm going to give them to you here in a 1, 2, 3 list, but perhaps you want to wait until I go through them a little bit more in detail to write them down at all. So just kind of give them to you all here at once. The three ingredients for a thunderstorm are moisture in the atmosphere, instability in the atmosphere, and a source of lift, which is simply something that gets the air moving upward. You've seen thunderstorm clouds grow, perhaps. If you look at them closely, you see they billow upwards. They start flat on the bottom, and they grow taller and taller and taller. And the taller they get, the more substantial and severe they might be. Well, something has to get that air started moving upward, and that something is considered a source of lift. And there are lots of different ones for that. So what I want to do is go through each of these separately and tell you a little bit about why each of them is important. So moisture's first. First of all, moisture is the key ingredient for a thunderstorm because it's the true fuel for the thunderstorm. It's where the energy comes from. To take water from a liquid into a gas, we have to evaporate it or boil it. Well, in the atmosphere, it's just evaporating. So as moisture is evaporating from liquid to gas state, that takes heat, just like boiling takes heat. Well, it's like you're storing that energy in the water vapor. And when you store it, it's like making the air into a battery for a thunderstorm, essentially. That heat energy is stored in the vapor, and when that vapor condenses into liquid or even freezes into ice in a cloud, that heat energy is released. And that's like the power that fuels the storm to continue growing taller and more substantial. So water vapor stores energy, which is released when air condenses that into a liquid or ice state. And then that energy, that heat energy, fuels the next stage or stages of the storm, which more or less equates simply to a very simple sort of mathematical idea. The more water vapor you have, the more storm potential you have for that storm to become large and potentially dangerous. The more water vapor, the more potential for a storm's strength to get to a severe stage and be damaging or even deadly. This is why the most severe thunderstorms tend to happen down south, where they're nearer to large sources of water vapor in the Gulf of Mexico and in the oceans as well. So the most thunderstorm days, if we had to look at the map of the United States and predict where do you suppose on 365 days of the year, which state has the most days that have at least a single thunderstorm in them? And I'm not sure what you'd guess. Most students would look at the map and perhaps guess places that they know are tornado prone, like Oklahoma, maybe Texas, Kansas. Those are all places you see a lot of on storm chasers. They get over into Arkansas and Missouri. They can get as far north as Nebraska. Storm chasers have even recorded episodes where they've gotten into North Dakota before and have even gotten into Montana. So there can be thunderstorms going a lot of places in the United States. But in the end, the most thunderstorm days, not tornadoes, but just thunderstorm days, are actually found in Florida, right along the Florida Panhandle. Actually, that's the peninsula of Florida. There's over 100 days with thunderstorms per year along that part of Florida. Why? Well, there's water everywhere, right? There's water vapor coming in from both the west side in the Gulf and on the east side in the Atlantic, and so there's a true source of fuel right there every day for the taking. If you think about thunderstorms as basically a summer weather time event, which they are, sure, Florida's got a much larger and longer summer than the rest of us do, but imagine 100 days of summer with thunderstorms. For us, that's every day of summer and then some. So basically Florida, central Florida there, gets some kind of thunderstorms every afternoon or every evening. I've been in Florida a couple times for Science Olympiad. I've been there with a conference time or two, and every time I've been to Florida, it's rained almost every afternoon and thunderstormed almost every afternoon, almost without exception. And then it's over and the night's beautiful. So Florida, thunderstorm heaven. Doesn't mean they get a lot of tornadoes, but they get a lot of thunderstorms. Now, the second ingredient is instability in the atmosphere. An unstable atmosphere, or to have instability, simply means that you have warm air at the surface and you have cooler air above. Why is this considered unstable? This is actually fairly normal. So normal and unstable sort of go together here. This is considered unstable because it allows air to continue to rise. So if we can get air rising, if it gets colder as you go up, that air will continue to rise because it will always be warmer than its surroundings. The opposite of this is what we just talked about in the last unit, and that was with inversions. An inversion would be a stable atmosphere. And if you want a storm to grow, if you want clouds to billow up and turn into thunderstorm clouds, then you want an unstable atmosphere, not a stable or inversion atmosphere. There, as you know, the air stays near the surface. That's the opposite of what we're looking for. So an unstable atmosphere will allow that air to rise and continue to rise and potentially get very, very tall. So as long as the surrounding air is colder than the parcel of air, which is the pocket of air that's going to make our thunderstorm, as long as the surrounding air is colder, this air in the middle can continue to rise and rise and rise. And as it does that, it cools and the air around it is getting cooler and it continues to go taller, probably until it gets to that tropopause. So as long as the surrounding air is colder than the parcel, or pocket of air, the parcel will be less dense and therefore can continue to rise upward. So instability in the atmosphere, kind of just the structure of the atmosphere vertically. And if the atmosphere in a local area, even if the air is very humid and full of moisture, if the air is not unstable, if the atmosphere is not unstable, a storm cloud just can't grow. So you can have 2 out of the 3 ingredients, and if the third one's not there, you won't get a thunderstorm, or you surely won't get one that's noticeable. The third and final ingredient then was that source of lift. We're going to go through several different kinds of sources of lift, but again, these are just things that get the atmosphere moving upward, or rather get the parcels of air moving upward, get them started. And it's sort of like a snowball going down a hill in a cartoon or an avalanche. Once you get it going, it kind of feeds itself. As long as the atmosphere is unstable and you get moisture flowing in, that source of lift gets it started, and that's just like turning the key, and the whole thing kind of goes from there. So the first source of lift is called differential heating. Differential heating just means that you'll have areas on Earth that get heated more quickly or get heated hotter than the areas nearby. And so if you have a hot spot on the Earth, it gets hotter and probably warmer faster than the air around it. So if you have a warm spot in the middle surrounded by cooler spots, that spot is the place where the air will start to rise first. And as it does that, that'll start the cloud building upward, and that's usually all it takes. It kind of a snowball effect from there. What you'll get and see then sometimes are these thermals, where you have a pocket of warm air rising on Earth. And there are large birds, lots and lots of large birds, that can glide on these thermals. They just stick their wings out and they let that warm air just push them up. They don't even have to flap. They just kind of float up there like a kite. And you'll see gliding birds do that on days when there's thermals in the atmosphere. It's also the same thing that hang gliders can take advantage of and actually ride the thermals and be able to just glide around and stay in the air for a long, long period of time. What kind of things can be differential heating on Earth? Well, it could be you have a wildfire in an area. So ironically, a fire can start a thunderstorm because, as you would guess, a wildfire is a very hot spot. We just had fires here not too long ago south of Bismarck, and those are very large, substantially large spaces that were burning, and they were very hot. So that could have been enough to get the warm air started upward over a fire, as you always see, and that would be enough. Another option, another opportunity for differential heating can be if a parking lot is large enough. A large parking lot like Kirkwood Mall's parking lot is pretty big. It's a lot of pavement, and pavement gets warm fast and it stores heat. So that can be a hot spot. Now, within a city, that doesn't work as well because really a whole city is pretty warm. But for that matter, a whole warm city full of concrete and pavement might be enough to start as a source of lift. And the final thing you see here is albedo-related locations. Albedo is a fancy word that just basically means whiteness. How white is a surface? Well, if you have a dark parking lot compared to, say, a lighter colored one, you might see a difference. If you've ever walked barefoot across blacktop, it's hot. I mean, ridiculously hot. And we've all felt this with something that's like a black car versus a white car. If you touch the hoods on those cars in a sunshiny day, there's a big difference. You burn your hand on a black car hood. So dark surfaces absorb more heat and get hotter. White surfaces reflect that light back and don't get nearly as hot. And there are differences on Earth the same way. Could be that grass reflects more light than, say, pavement. Could be that water certainly reflects a lot of light back. Snow reflects a lot of light. Probably not an issue with thunderstorms, but snow is almost 100% reflective if it's nice, clean, white snow. Another source of lift can be terrain. So if you have a mountain range that forces air to go up and over the mountains, a lot of times it sort of acts like a ramp. And as warm air kind of goes up and over a mountain range, it doesn't just go up and then down and over the other side. It often can start going up one side of the mountain and just keep on rising as it continues on. And that can make a thunderstorm coming off the backside of that mountain perhaps. Or even on the slope as it's rising up, you can have thunderstorms start to grow on the upside of the mountain range as well. We don't have a lot of mountains in North Dakota, but even some sort of ridges like you find with the Killdeer Mountains could potentially kick up some thunderstorms. This is probably the least common source of lift in North Dakota because we just don't have much for terrain. And where we do, like the Badlands, it's a downward terrain, not so much an upward mountain range or something like that. Finally, sources of lift that are quite common are these, and they're weather-related sources of lift instead of geography-related things. Fronts. Well, we've talked about fronts already. Fronts are either cold fronts or warm fronts, a place where cold air is making warm air go up. Of course, a little front then can cause warm air to rise, and that's a lift source. So if cold air is pushing warmer air up on a small scale, that can lead to thunderstorms. We also can find dry lines. Dry lines are kind of like fronts, except it's not cold versus warm air forcing the warm air up there. It's actually dry air and moist air, where dry air forces moist air to rise. And of course, if we know it's moist air, that's the fuel. So in the southern plains, there's a lot of places where hot, dry air will come off, say the southwestern desert area, New Mexico, Arizona, Colorado, Utah. Hot, dry air coming across. And then on the other side, we've got warm, moist air coming up from the Gulf of Mexico. So it's not cold and warm like we'd find in a front, it's dry and moist. And dry air is very dense compared to moist air, and it forces that moist air to rise up. And that's why we get so many thunderstorms and tornadoes across the southern plains, because it's where dry lines kick up. And when if you're paying attention on storm chasers, you'll hear them talk about dry lines fairly often. Final source of lift then is an outflow boundary. And this is sort of a chain reaction idea, that one thunderstorm, as you'll hear later on with anatomy of a thunderstorm, there are cold wind gusts that blow down and out of a thunderstorm as it produces rain and even hail. That cold wind gust can flow across the earth for miles and kick up another storm nearby. So one storm's kind of exhaust almost will flow over here and kick up another storm and start the next one. So one starts the next. And occasionally, if you're looking at a thunderstorm severe weather radar, you'll find thunderstorms in a line with the large one and then a smaller one, smaller one, smaller one. And it's often the case that the first one got going and it's fueled the start of the next one, and that one started the next, and it's sort of a chain reaction. And those can form into a long line of thunderstorms, which can get very, very severe. The next thing we're going to look at is going to go on to the actual anatomy and the stages of drawing a thunderstorm out, sort of show you how they start as small storms and they can grow into a larger storm if things are right. But this map sort of shows you fronts where cold air is meeting warm air. You can see it here kind of across the southern Rockies. Cold air is meeting warm air. That would be considered a cold front. And in the middle then, what I was telling you about, where we see warm, dry air coming up off the desert and warm, moist air coming off the Gulf. And where they meet is a dashed line we'll see here called a dry line. It's the boundary between dry and wet, or dry and moist air. So cold fronts and dry lines are probably the most common as far as these fronts and dry lines kicking up thunderstorms. That's it for the key ingredients. The next video we'll talk about the 3 stages of a thunderstorm's development, and your third and final video we'll talk about tornadoes and the anatomy of thunderstorms inside.